In the previous module, we introduced matter and discussed how it forms everything in the universe. Under matter comes the substances and the mixtures. We discussed the differences between the substances and mixtures and said that we can add substances together to form mixtures using physical change. We can also separate mixtures into substances using physical change as well. Substances can be either an element or a compound. We then discuss the elements and introduce the periodic table. Elements can join together to form a compound in what we call a chemical change. Compounds can also break down into its elements in a chemical change too. We have two types of compounds, molecular and ionic. We also have two types of mixtures, homogeneous and heterogeneous. Now, let's move on to Module 3. Today's topic is related to the atomic theory and structure. Module 3 will be covered in 3 videos. In the first video, we will discuss Dalton's model of the atom and the different laws of this model. We will discuss the subatomic parts, or the components of the atom, and then discuss the Rutherford Model of the atom, or what is called the nuclear atom. This will lead to the concepts of isotopes and atomic mass. The second video will mainly cover the energy related to the electrons. So we will start with the electromagnetic radiation concept, and then discuss the Bohr atom model, which will lead to the energy levels of electrons. Finally, we will discuss the relationship between electron structures and the periodic table. The third video will discuss the naming system for ionic and molecular compounds, or what we call nomenclature of inorganic compounds. The learning outcomes of the first part of Module 3 are: explain Dalton's model of the atom, identify the subatomic parts of the atom, explain the Rutherford model, explain the concepts of isotopes and solve the related questions, and explain atomic mass. As we said in the introduction, we will discuss the atomic theory and structure in this module, and to do that we will start with Dalton's model of the atom. Dalton's theory can be summarized as follows. Elements are composed of minute indivisible particles called atoms. Atoms of the same element are alike in mass and size. Atoms of different elements have different masses and sizes. Chemical compounds are formed by the union of two or more atoms of different elements in a fixed ratio. Also, atoms may combine in different ratios to form more than one compound. Dalton believed that atoms are the smallest particles in our world and that we cannot split them. However, we now know that this is not true, and we can split atoms into different elements. Dalton's theory includes two laws. The first is called the law of definite composition. This law states that a compound always contains two or more elements that are chemically combined in a definite proportion by mass. For example, a water molecule has 3 atoms with the ratio of 1 oxygen to 2 hydrogen atoms. But what is the mass ratio of oxygen in relevance to the hydrogen in a molecule of water? The ratio in this case is 1 to 8. So if you have 1 gram of hydrogen, then you have 8 grams of oxygen. Also, if you have 16 grams of oxygen, then you have 2 grams of hydrogen, and so on. It is important to note that hydrogen and oxygen may have different ratios in a different compound. For example, the compound hydrogen peroxide has 2 hydrogen atoms and 2 oxygen atoms, so the ratio is 1 to 1 in this compound. In terms of the mass ratio, if you have 2 grams of hydrogen, that means you have 32 grams of oxygen. The second law is called the law of multiple proportions. It states that atoms of 2 or more elements may combine in different ratios to produce more than one compound. Let's look at some examples in the next slide. This table lists compounds that consist of the same elements but with different ratios. For example, copper chloride and copper 2 chloride have a different composition or ratio, and this is because they are two different compounds and have different physical and chemical properties. Now let's move to the subatomic particles. Here we will cover what is inside the atom. Atoms are very small in size, and therefore we use small measuring units. For example, a single atom diameter ranges from 0.1 to 0.5 nanometers. Remember that 1 nanometer equals 10 to the power of negative 9 meters. In chemistry, we normally express atom sizes in a convenient way using the measuring unit called an angstrom, and it has the symbol of a capital A with a small circle on top. 1 angstrom equals 10 to the power of negative 10 meters, so we can say that atom sizes range from 1 to 5 angstroms. You don't need to remember the conversion factor for the angstrom unit, as it will be given to you in the exam if needed. We have 3 particles inside an atom, and they are electrons, protons, and neutrons. You can see that electrons are negatively charged, while protons are positively charged, and neutrons are neutral with no charge. The mass of these particles is very small. For example, a proton has a mass of 1.673 times 10 to the negative 24 grams. Neutrons have a similar mass. Electrons, on the other hand, are approximately 10,000 times lighter, and therefore we ignore the mass of electrons when we calculate the mass of an atom. We also do not take into consideration the change in an atom's mass that happens due to losing or gaining electrons, as this change will be very small. Let's discuss how these 3 particles are distributed in the atoms. To do that, we need to understand nuclear theory, or the Rutherford Model. Before Rutherford's experiment, J.J. Thomson proposed a model to explain the structure of an atom where he imagined that electrons are distributed around the atom like seeds in a watermelon. However, Rutherford conducted an experiment to explain the atom model where he sent alpha particles, which are positively charged, through a thin gold foil. Rutherford noticed that some particles went through while others bounced back. So Rutherford rejected Thomson's model and suggested his new model, which is called the nuclear atom. Rutherford discovered that atoms have a nucleus in the middle with the electrons circling around it. He suggested that the nucleus contained only protons and neutrons. Rutherford claimed that the size of the nucleus is 10 to the negative 4 angstrom, so it is almost 10,000 times smaller than the atom. The remaining size of the atom is an empty space, and that's where the electrons circle around the nucleus. He also suggested that the positive charge coming from the neutrons is neutralized by the negative charge from the electrons when the atom is neutral. The number of protons, or what is called the atomic number, determines the identity of the element. We mentioned that the mass of the atom comes mainly from the protons and neutrons, and we ignore the mass of electrons as it is very small compared to the other 2 particles. In nature, we find that atoms with the same elements might have different masses. If we examine those atoms, we see that they have the same number of electrons and the same number of protons, but have a different number of neutrons. For example, there are 3 isotopes of hydrogen. They all have 1 proton and 1 electron. The first isotope has 1 electron and 1 proton, but no neutron, so this hydrogen has an atomic mass of 1. the 1 proton plus 0 neutrons, and is called protium. Another hydrogen isotope that we find in nature has 1 electron, 1 proton, and 1 neutron. So the atomic mass of this hydrogen is 2, the 1 proton plus the 1 neutron, and it is called deuterium. The last isotope for hydrogen has 1 proton and 2 neutrons, so the atomic mass of this isotope is 3, and it is called tritium. The most common isotope that we use in this course is the hydrogen 1 atom. There is a conventional method to present the isotopes, and this is what we call the Nuclide method, the Nuclide symbol, or the isotopic notation. In this method we have 3 values. First, the symbol of the element. On the top left of the symbol we find the mass number, which represents the sum of the protons and neutrons in the nucleus. On the bottom left we find the atomic number, which represents the number of protons only in the nucleus. Let's look at carbon as an example. Carbon has the symbol C. There are many isotopes of carbon, but we will consider only 2 in this example. The first isotope has the nuclide symbol of C, 12, and 6. This means that there are 6 protons in this carbon and 6 neutrons. The second isotope has the symbol C, 13, and 6. This means that there are 6 protons and 7 neutrons in this carbon. It is acceptable to report the isotopes using the mass number only, so we can say carbon 12 or carbon 13. The reason is that the atomic number forms the identity of the element, and you can access this information from the periodic table. In the periodic table, the atomic number is written on top of the element. For example, carbon has number 6. So we can say that carbon is the element number 6, and it has 6 protons. You will never see a carbon atom with 7 protons. Let's practice this concept before we proceed any further. In this table we have the chlorine 3717 isotope. From this nuclide symbol we can determine that the atomic number of chlorine is 17. The mass number is 37. By now, you should know that the number of protons is the same as the atomic number, which is 17. Now, to determine the number of electrons, we look at the symbol again. Is there any positive or negative charge here, or is the element in the neutral state? As the chlorine in this example is in the neutral state, then the positive charge, the proton, equals and opposes the negative charge, the electrons. And because we have 17 protons, then we should have 17 electrons. Finally, to determine the number of neutrons, we deduct the number of protons from the mass number. So 37 minus 17 equals 20, and that's how many neutrons we have in this isotope. Please pause this video and practice filling the table for the other 2 examples. The answers will be displayed after you continue. In the argon example, you need to find the isotope from the given information. You have the atomic mass of 18 and 20 neutrons. Please pause the video and try to fill in the table by yourself. Remember to practice this concept further using the textbook and workbook questions, and we will go through many examples in the tutorial session. We mentioned in the recent slides that the atomic mass of an element refers to the mass of protons and neutrons in this element. We also mentioned how these particles have very small masses, so it won't be convenient to use kilograms as the SI unit to express the mass of elements. For example, the mass of a hydrogen atom is 1.673 times 10 to the negative 24 kilograms. Therefore, scientists agreed to use a different unit to express the atomic number of elements. This unit is called AMU and is defined in relation to carbon-12. So the mass of one atom of carbon-12 is equal to 12 AMU. Please note that this is an exact number and significant figures do not apply in this case. Let's look at some examples from the periodic table. The atomic mass of hydrogen is 1.00794 AMU. The sodium atom has an atomic mass of 22.989 or approximately 23 AMU. You might wonder why the atomic mass is not a whole number. The reason is that this mass represents the average mass of all the isotopes that exist in nature. The average mass presented in the periodic table is calculated by multiplying the atomic mass of each isotope by its abundance in nature and then adding the results together. For example, copper has two isotopes, 62.9298 and 64.9278. The 62.9 isotope has an abundance of 69.09% in nature, while the 64.9 isotope has an abundance of 30.91%. So to report a representative copper in the periodic table, we calculate the average of the two isotopes, taking into consideration their abundance in nature. To calculate the average of copper, we do the following calculation. 62.9298 AMU times 0.6909 plus 64.9278 AMU times 0.3091 is equal to 63.55 AMU. And this is the atomic mass that you will find in the periodic table. There will be more examples to practice this concept in the tutorial. This is the end of video 1. Please proceed to the second part of module 3 and watch video 2 that will discuss the electrons and the different energy levels.